This screencast is on how variables relate to one another and how we can describe our results from an experiment. So first we're going to talk about accuracy versus precision, and it's easiest to think about it in terms of a game of darts. In this particular game you have 3 trials to shoot for the bullseye. So our first one looks like this. Here's our second one. And the last one is kind of how I play darts. Alright, we would describe the first one as both accurate and precise. The second dartboard is precise but not accurate. And the last one is neither accurate nor precise. So how could we identify or define accuracy and precision? Well, if you look here, this is both accurate and precise. All 3 trials hit right about the same point, and they were very close to the bullseye, which is what we were going for. This one is just precise, so all 3 hit in the same place, but they're nowhere close to the bullseye. So we can say that accuracy is how close we are to our target, or what we were, the accepted value or correct value. And precision is how consistent we are. In a chemical or any sort of scientific experiment, when you do something the same way, it should be repeatable. You should get about the same answer. This is neither accurate nor precise. Even if I had a dart that hit the bullseye and the others landed where they are right now, then we still would not call that accurate. You can not have accuracy without precision. That one would just be lucky. So here are the definitions. You can pause the screencast and write these definitions down. Just remember that when I ask you on the test about accuracy and precision, I want you to use these definitions. Direct proportion is how we can describe the relationship between 2 variables, or at least a possible way. If the variables, when you graph one against the other, result in a line like this, or a linear graph, we would say that it is those 2 variables are directly proportional. If you'll notice in this one, mass and volume, as my volume goes up, so does my mass. So these variables move in the same way. You need to sketch this graph very quickly, and you don't have to write my example down, but as one variable increases, so does the other variable. The variables move in the same direction, and they form a linear graph. Inverse proportion. When you graph one variable against the other, you get a shape that looks like this. When one value increases, the other variable decreases. So if I go back to this graph, this is volume and pressure, and we'll talk about that when we get to gases. If my volume is at 500 cubic centimeters, my pressure is right around 100 kilopascals. If I cut my volume in half, my pressure doubles to 200 kilopascals. So again, when one variable increases, the other variable decreases. And again, you don't have to write my example. They form a hyperbola when graphed. You are going to need to know the graphs of both direct and inverse proportion, the shape of those. Last but not least is how we can calculate the accuracy of experimental value to kind of tell us how close we were to what we were trying to get, to our target. And this is done through percent error. Percent error is accepted value minus experimental value, and you take the absolute value of that number, so no negative numbers there. And you divide that difference by the accepted value, and then multiply that entire answer by 100 to make it a percent. So the way I remember this is accepted values are checked multiple times, because these are the ones you would look up in a book, the accepted or correct value. And so that's the one that's in the formula twice. Experimental value would be the one you got in lab.